Hi everyone. It's an honor to be here to introduce our recent work, PBE-CC, Congestion Control via Endpoint-Centric Physical Layer Capacity Measurements. This is Yaxiong from Princeton University, and this work is a joint work with my colleague Fan and my supervisor, Kyle Jamison. We know that nowadays there are a large number of cellular connected devices. According to the Cisco annual report, there are around 5 billion mobile subscribers in 2018, which covers around 66% of the global population. Among all the subscribers, 3.7 billion of them are LTE users. In total, we have 8 billion mobile devices in the world. Providing high-speed and low-latency internet for those mobile subscribers is highly desired, but also very challenging. To guarantee high speed and low latency, we need a robust congestion control at the transport layer. If we model the transport layer connection as a pipe, then the size of the pipe is determined by the bottleneck capacity. The design goal of modern congestion control algorithms like BBR is to match its sending rate to the bottleneck capacity. This job became very challenging in cellular network, as most of the time, cellular wireless last hop is the bottleneck whose capacity varies significantly and rapidly. Before answering why the capacity varies, we need to look at two parameters that determines the capacity. The first parameter is the allocated bandwidth. Both 4G and 5G adopts OFDMA, which divides the time into subframes and the frequency into blocks called physical resource block. The base station implements a resource allocation algorithm to allocate different number of PRBs to different users according to their data pattern. And this allocation is different across subframes. The second important parameter is the wireless channel quality, which determines how many bits that can be carried inside one PRB. The base station implements rate adaptation algorithms to select the physical layer configurations like the modulation and the coding schemes. Depending on the selected modulation and the coding scheme, the number of bits inside one PRB can be as small as 16 bits or as large as 900 bits. The capacity depends on these two parameters, and these two parameters varies in practical cellular network. Typically, a base station can serve hundreds of users simultaneously, and all those users have different usage patterns, so you can imagine that the bandwidth allocation in cellular network is highly dynamic. The wireless channel quality of a specific user changes with the mobility of the user. And the mobility of the user is actually quite common in cellular network. What makes things worse is the carrier aggregation. Both 4G and 5G support carrier aggregation so that one mobile user can talk to multiple base stations simultaneously. As a result, you can see that this user experiences all the dynamics of all its aggregated base stations. So estimating the capacity of the cellular link is very challenging, and relying on the end-to-end metrics like RTT, packet loss, and packet time steps cannot track such a fast varying capacity. We observe that this job is challenging, but it's possible. All the information we mentioned before, like the resource allocation, carrier aggregation, and MCS index, they are all broadcasted by the cell tower. The cell tower has data channel to deliver data. It also has a dedicated control channel to deliver all the information to the mobile user. Most importantly, the data channel is not encrypted, which means a mobile user can decode every control message sent over the control channel. Therefore, we observed such an opportunity that if we enable the mobile endpoint to snoop on the cell tower, the endpoint can immediately know the detailed congestion states without any infrastructural changes required. So based on our observation, we propose PBE. The architecture of PBE is presented in this figure. The server sends data packet to the mobile client, and the mobile client estimates the cellular link capacity and feed it back to the server. The server extracts the feedback and matches its sending rate to the estimated cellular link capacity. So here, an important question to be answered is, how does the mobile client estimate the capacity? We actually estimate the capacity when a user starts a flow using this equation. In this equation, the PCL is the total number of PRB that one base station has. This is a constant. The N is the number of mobile users that shares the bandwidth. Even though a base station serves hundreds of users, but only several of them is active at each specific time period. And the RW is actually the wireless physical data rate, which can be derived from the MCS index. So according to the equation, we know that all the users will equally share the bandwidth when they start their traffic. If there's only one user, this user will take all the bandwidth according to this equation. If there are two users, these two users will share the bandwidth equally. And it is the same for the three user case. After the start, we will enter a steady state. In the steady state, we use a different equation to calculate the capacity. To explain some parameters in this equation, I will use the following example. In this example, the base station allocates this amount of PRB to the PBE user, and this amount of PRB to all the other users. And you can also observe that there are some PRB not allocated for any user, so they are idle. In this equation, the P idle is the total number of idle PRBs the base station has. The PA is the allocated PRB for this PBE user. And RW and N are the same as they are in the previous equation. So from this equation, we observe that all the users will get an equal portion of the idle capacity. I will use two detailed examples to show what does this means. In the first example, we first have two users, user 1 and user 2 share the bandwidth. The third user comes in and ends its transmission in the third subframe. So in the first subframe, we observe idle PRBs. The user 1 and the user 2 immediately detect the existence of the idle PRB by looking at the decoded control message. And then they will occupy the idle PRB equally. Similarly, if the third user didn't end its transmission in the fourth subframe but became app-limited, which means it doesn't have enough data, still we will observe idle PRB appear. And similarly, user 1 and user 2 will occupy this idle PRB immediately after its appearing and equally. So according to the above analysis, we could see that our client can immediately detect any emerging idle capacity and inform the sender to increase the sending rate and grab the fair share portion of the idle capacity. After we introducing the capacity estimation algorithm, we need to handle another problem. So our estimation algorithm only estimates the capacity of the cellular link. What if the bottleneck switches from the cellular link to the internet link? How shall we handle such a case? A Stallman solution would be blindly matching the sending rate to the capacity of the cellular link. This indeed works if the cellular link is indeed the bottleneck. So we will have the sending rate equals to the achieved throughput, and no packet will be buffered in the network. This is called the CleanRock's operating point, which is proven to be theoretically optimal. But if the bottleneck is at the internet link, then the sending rate will be larger than the capacity of the link, than the capacity of the bottleneck, and the achieved throughput will be smaller than the sending rate. Obviously, there are some packets buffered in the network. As a result, we will observe the increased delay or even packet drops. So we really need an algorithm that can detect the switch of the bottleneck, and we should take different actions when the bottleneck is at different location. A natural question is, how can we detect the switch of the bottleneck? As we introduced before, when the bottleneck switch from the cellular link to the internet link, we will observe the increase of the delay. Can we simply use the delay increase as a signal of bottleneck switch? It doesn't work in practice because we observe a lot of sudden delay increase. This sudden delay increase is not because of some random reasons. It's actually caused by the reordering operation at the mobile client side. Specifically, cellular network use transport block to deliver packets to the mobile client. Each transport block could contain one or multiple transport layer packets, like multiple TCP packets, for example. If this transport block is correctly received, all the packets inside the transport block will be reported to the transport layer. If a transport block gets lost, the mobile client will buffer all the subsequent transport block in the reordering buffer until the originally lost transport block is retransmitted. If the retransmission succeeds, all the buffered packets will be reported to the transport layer together. As a result, we can see that one-time retransmission can cause 8 millisecond delay, and the one transport block can be retransmitted 3 times at most. Therefore, we define a thresholding delay, which equals to the propagation delay multiplied the delay equals to maximum 3 retransmissions. And we also consider the 3 millisecond network jitters. So our algorithm is that we will detect a switch if the one-way packet delay exceeds the threshold delay. So we detect the switch of the bottleneck. What shall we do if the bottleneck is at the internet link? We actually did exactly the same as BBR do. Specifically, BBR set the sending rate to the achieved throughput. This algorithm has a problem. When the bottleneck capacity, which is also the capacity of the internet link, increases, the sender doesn't know. So the sender cannot increase its sending rate accordingly. As a result, PBR will probe for any possible capacity increase. Specifically, it divides the time into 8 cycles, and the sender will increase its sending rate blindly in 1 cycle. If the increase of the sending rate causes the increase in the final achieved throughput, we are safely to say that the capacity of the bottleneck link increases. So we can safely increase our sending rate without causing any buffering. We change this behavior. We change the probing behavior of the BBR to a wireless-aware BBR-like probing. Specifically, we set the probing sending rate to a minimum of 2 numbers. The first number is the 1.25 multiplied the current throughput, which is the standard parameter defined by the BBR. The second number is the capacity of the cellular link. We do this because when the internet link capacity increases a lot, and the sender probe, we want the sender to stop at the capacity of the cellular link. And if the capacity of the cellular link is achievable, then we can safely say that the bottleneck is switched back to the cellular link because the capacity of the internet link is larger than the cellular link. So we switch back to handle the bottleneck in the cellular link. So till now, we finished the introduction of our design. And next, I will pass the talk to my colleague and co-author of this paper, Fan to introduce the implementation and evaluation.
Thanks, Yashun. Here we talk about the implementation. We have a practical problem that programming a mobile phone to snoop on cell towers requires customization of the phone's firmware. But the code is closed source. So we built an open source prototype on USIP to bypass this problem. These two figures show our system structure and systems picture. Here I want to note that we use 3 USIPs for experiments to listen to 3 cell towers simultaneously. We configure Amazon servers as the PBE-CC senders. We use 3 mobiles, Samsung, Xiaomi, and Redmi as our mobile clients. They are able to aggregate 3 cell towers, 2 cell towers, and 1 cell tower respectively. We compare our algorithm with 7 other algorithms. We first introduced the throughput and delay performance for static users. We choose 40 locations covering all combinations of indoor or outdoor, 1 or 2 or 3 aggregated cells, busy or idle network conditions. At each location, we repeat the experiment with different congestion control algorithms for comparison. Here is the results among those high throughput algorithms. These are the throughput and delay CDF of BBR over 40 locations. Then we measure the throughput and delay of Virus at the exact same 40 locations. We can see that Virus has high throughput but high delay. Next, we show the performance of Cubic. Sometimes it has a high throughput and a high delay, and sometimes it has a low throughput and a low delay. But for PBE, we can see that it simultaneously achieves high throughput and a low delay. Here we show the detailed comparison among all 8 algorithms. We present the throughput and delay in the same figure, and we can see that PBE is always located at the top right corner of all the figures, which means it achieves high throughput and low delay. Then the performance of VR, Virus, and Cubic is consistent with our previous CDF plots. Other algorithms like Coupa and PCC achieve low delay, but they have low throughput. I also want to note here that the number beside each algorithm is the number of triggered cell towers. In general, more cells triggered means a higher throughput. In this experiment, PBE, BBR, and Virus triggered all supported cells, so they have higher throughput than others. We also tested the performance for mobile users. In this experiment, we moved the mobile phone along a predefined trajectory, where the signal strength decreases and then increases. The left figure shows that, in general, PBE achieves high throughput and low latency. In the right figure, we compare the performance of PBE and BBR along time. We observe that PBE can maintain low latency by responsively adapting its sending rate when the channel quality changes, but BBR cannot. We also evaluated the performance and the controlled computation. In this experiment, besides the testing phone, we have another mobile phone sending periodic competing traffic. In the right figure, the highlighted parts show the time when the competing traffic come in. And we can conclude from this figure that PBE can swiftly react to the competing traffic to maintain its low latency, although there are some bursts. But BBR cannot react fast enough. At last, we introduced the fairness. In this experiment, we use 3 mobile phones as 3 competing users, and they all share the same primary cell. 2 of them run PBE, and the other runs BBR or Cubic. We start their data traffic at different timestamps. We can see that PBE can fairly share the bandwidth when other flows exist.
To conclude this paper, we implement the first end-to-end congestion control to seamlessly integrate mobile client-side wireless physical layer capacity measurements into its design. This is crucial for the multi-cell design of 4G and 5G cellular network. Our system outperforms BBR, Cubic, COPA, and many other leading congestion control algorithms in both latency and throughput. Specifically, we achieve 6.3% higher average throughput than BBR, while simultaneously reducing 95 percentile delay by 1.8 times.